Section 9.2 is all about the confidence interval for the mean. And for the confidence interval for the mean, we have to introduce a new distribution that we haven't talked about yet, which is called the t-distribution. Now, the t, I'm not sure what it stands for, but you may hear this distribution called a student t-distribution. A lot of people nowadays just call it the t-distribution, but the name student actually comes from the person who discovered it, who was a student at the time. It was around 19 around the 1900s, early 1900s. Gossett was his last name, and he actually worked for Guinness Brewing, but he developed this distribution and the statistical tests that go along with this distribution. Now, the t-distribution is something that we're going to mainly use in the background, and it's closely related to the normal distribution, but it's just slightly different. So I just want to talk a little bit about it, just so you've heard it before. Now, if you have a normal distribution x with a mean mu and a standard deviation s, if you make this transformation of the sample mean, then you get a t-distribution, and it has degrees of freedom n minus 1. Now, the degrees of freedom are a measure that control the shape of the t-distribution, and the higher the value of the degrees of freedom, the closer the t-distribution gets to the normal distribution. So I have a bunch of properties here. You don't really need to memorize these, but here's just a picture of a couple t-distributions. So this one here, the black one here, is degrees of freedom 3. You can see it has a generally like a bell-shaped curve. It's just thicker in its tails. So on the tails over here, they're higher up than the normal distribution. And then degrees of freedom 5 is here. It's getting closer as the degrees of freedom increase. And when you get to degrees of freedom, even like 50, it's hard to tell the difference between the normal distribution and the t-distribution with degrees of 50 visually. You can't really see it. It's hard to see. But anyway, this is going to be used mostly in the background. There are what are called critical t values, just like the critical z values we have in the proportion with the normal distribution, that standard normal distribution. We have an equivalent thing with the t distribution, and these are typically larger values than the critical z values. Okay, now before we actually use the t-distribution, I want to go through a quick example to hopefully make a connection to what we did in chapter 8 and to the confidence intervals we're developing in this chapter. So it says, suppose that x is a normal distribution of weights of acorns from your family's oak tree. The population mean is unknown, but you know that the population standard deviation is 0.3. Now, that assumption there, knowing the population standard deviation, that's not very likely, but we could just assume that they know it. You measure the weights of 50 acorns, and you find that the sample mean x bar is 3.25 grams. And this first part says if we assume that x bar is a very close estimate of mu, draw a picture of the x bar distribution. Okay, well, x bar we know is going to follow a normal distribution, or it's going to get close to a normal distribution because of the sample size here. It's a high sample size. So it's going to look mound-shaped and symmetric. And it's going to be centered at 3.25. And n is equal to 50. So the standard deviation would be that 0.3 divided by the square root of 50. I plug that in the calculator and it gives me 0.042426407. And this would be the sampling distribution for the mean. Okay, now it'll look normal, close to normal, but part B asks us to use this distribution that we just made, use this distribution in order to find a value centered around 3.25 grams that would consist, or values around 3.25 grams that would consist of 95% of the distribution. So doing a similar thing, so I just want to draw the picture. We have it centered at 3.25 and we want a value here and a value here so that this area in between is 95%. Okay, now how would we get those two values? Well, in the past we'd say let's use the inverse normal distribution Excel file. And we're going to put the mean and the standard deviation that we have in part A, these two here, well, the 3.25 and in this number here. I'm going to plug those in with the probability of 0.95. And it will then give us our upper limit and our lower limit. So going to inverse normal, here it is. The centered at 3.25. Standard deviation is 0.3 divided by the square root of 50. I'm just going to plug that in as a formula to not lose any decimal places. So plug it in like that. And the probability is 0.95. It gives me these two values, 3.16, and a few more decimal places. I'm going to do 668, and then 3.3332. Okay, now you may be saying, oh, lower limit, upper limit, that feels like a confidence interval. And yes, you'd be right. There are a few differences because we're not going to be using the normal distribution for this situation, but it ends up being really close when we use the t-distributions. But I wanted to give you an idea of what's going on in the background with these confidence intervals. And they really are using the inverse distribution in order to get these two limits and to give us a confidence. Yeah. Okay, so for the mean, there's a set of instructions that I have here. And just like for the proportion, we have three parts: the conditions, the computing, and then interpreting. And conditions are similar. The normal criterion is different though. So you have to be careful with that. If the original distribution is normal, you're good to go. If the original distribution is not normal, you should check that the sample size is large enough and is greater than or equal to 30. In that case, we're good to go. If not, then you'd note the sample size isn't quite large enough for us to fully trust the results of this confidence interval. For the computing by hand, sometimes this is a little bit more of a process by hand because you have to compute the mean and the standard deviation, and we know, especially with the standard deviation, that's just very time consuming if you do it by hand. So I don't want you to do these things by hand. I just want you to use the technology. If you ever have to, you have reference to these notes, hopefully, and you can say, oh, okay, now I have to do this by hand, and it's going to be a little bit of a pain. I doubt that you'll have to do it by hand. Lots of stats teachers have been moving away from doing things by hand and really having students learn the technology, because that's what you're going to be doing out in the real world. If you start doing a standard deviation by hand at your workplace, your boss is going to be upset because you're just wasting time. You should use technology. But yeah, it's here if you ever have to use it. We're going to use the Excel file confidence intervals again, and it's a little bit trickier to use. I'll show you when we get there. There's two different cases when you get into the file and into the sheet, that specific mean sheet. So you have to be a little bit careful. So let's actually do one. So it says a company has a new process for manufacturing large artificial sapphires. And this company produces thousands of sapphires each day. And in a trial run, 27 are randomly selected. They know from experience that the distribution of weights is normally distributed. That's good. The sample mean weight for these 27 gems is 6.75 carats, and the sample standard deviation is 0.33 carats. And we want to make a 95% confidence interval for the population mean mu. So our first step is to check conditions, just like last time. Check conditions. Definitely an important step. The first one, random sampling. Okay, it says randomly selected. That's good to assume that they've done random sampling. So I'll write that there. Random sampling is used. Now, for the normal criterion, up here, you have two different cases. If the original is normal, we're good to go. If not, we need our sample size larger than 30. This one says the original is normally distributed. That's great. That means we don't need the condition that it's over 30. I can just put the original distribution is normal. So the sampling distribution is normal, which is good. It meets that criteria. Now, the third one, independent sampling, 27. That's a pretty small sample, and we're looking for that to be less than or equal to the 0.05 times the capital N. In this case, they're saying thousands. So they make thousands of sapphires. And even if we take, even if we would take 1,000, I think we're all right. Times 0.05. Yeah, 5% of 1,000 it's 50, so that's already bigger. And they're saying thousands, so more than just 1,000. So it's even smaller than 5%. So this is good. We can say the sampling is independent. Okay, great news. Our conditions, all three of our conditions are met. That means we can compute. In this class, I want you to use Excel. So I'm just going to use the confidence intervals Excel file. And we're going to use the mean sheet. And we're going to use, there's one last thing, use the left side for the statistics. There's kind of two different situations. I'll show you the other situation in the next example. But let me show you what this Excel file looks like. So not this one. Here. Make sure at the bottom, changing the sheet to mean, super important. And here are the two sides that I'm talking about. So when you have statistics you want to do the left side. If you're given the data, you would use the right side. So we're using this side here. So we need to fill in these 4 different things. We need the sample mean. And I'm going to let the Excel file guide me. I'm going to write down these symbols and then I'll go back and look for them in the wording of the problem. I need the sample standard deviation S. I need the confidence level. And then I need the sample size N. Okay, so going back, we can identify what they have given us now. So just reading through it, the 27 sapphires are randomly selected. That's the sample size. The sample mean, they say, is 6.75. This one here. Sample standard deviation, that's S, 0.33. And then they want us to construct a 95% confidence interval, so 0.95. Now we can go back to the Excel file, plug those in, and once we have those in, it does our computations for us. The critical t value is here. So if the homework asks for that, it comes up in the file itself. Margin of error, and then our lower and our upper limits. Those are what define our confidence intervals. So I gotta copy those down. So 6 point, I'll just do 3 decimal places, 619 and 6.881. Okay, one last step. We gotta interpret what this is telling us. And put a line there. So if you're not super comfortable with this statement, you can look back up here. We can say, or we are confident, C% confident that the population mean is between those two. So I can say we are 95% confident that the population mean weight of artificial sapphires is between 6.619 and 6.881 carats. Okay, so a fairly similar process from one situation to another. Definitely a lot of like terminology that you need to be aware of. The last test isn't cumulative, as in it'll focus on the last third of the class, but you can tell, like, if you don't know what these symbols mean, well, not that one, but like N and all of those, if you don't know what the symbols mean or like what we're actually looking at, then it's nearly impossible to get through this last third. But yeah, let's look at this one here. So it says that a doctor wants his patient to track his blood pressure for 2 weeks. The patient records his blood pressures in the table below, and we can see those. Note that the first number is the systolic blood pressure, second is the diastolic, and it specifically says don't check the conditions for creating a confidence interval for the mean in this example. Okay, so they're saying don't check the conditions, probably because they don't meet the conditions, which sometimes they don't, but they still want us to create a confidence interval. So we're gonna go along and just still do the confidence interval. So it says calculate the 95% confidence interval for the patient's systolic blood pressure. And I want to write here just how we're going to do this. And we're going to use the confidence interval Excel file. And we're going to use the mean sheet. And we're going to use the right side for the data. Okay, we plug in the data. And the only other thing to plug in is that C is 95%, 0.95. And once we have that plugged in there, we're going to have our lower limit and our upper limit. So a fairly quick process, especially if you have the data typed out already, which I did beforehand. So I'm just going to take the systolic blood pressures here, make this a little bit bigger. Take these systolic blood pressures, gonna copy and paste into the mean sheet. The data is on the right side here. And I'm just gonna keep it formatted the same. Make sure you get rid of this. If you have extra data, you gotta get rid of it. So you plug the data in here. It does a bunch of calculations for us. The sample mean is here. Sample standard deviation is here. Don't touch those. The confidence interval is something we can plug in. Does the sample size for us? Yep, looks like 14. Critical value, max error, and then the thing that we need to report, those two things there, 121 point, I'll round to just one decimal place, 121.8 and 128.5. Okay, now we do a very similar thing for the diastolic, so I just want to do that right away while I have the Excel file open. And we just copy and paste the data. Here, taking diastolic now, copy that, paste it, let's do values, good. Once we have that pasted, we can just double check everything looks good, and it's calculating our lower and our upper limit for us, 78.4 and 83.8. So fairly quick once you get a handle on it. And this is typically how, like, if you're crunching a lot of numbers, you make things, you create things that, like, tools to help you to do these things in a quick way. Yeah, so the interpretation here, they didn't really ask for an interpretation. We're just calculating the limits, but you could think this is with 95% confidence, the systolic blood pressure average will be between those two numbers. With 95% confidence, the diastolic blood pressure average will be between those two numbers there. Now, it says if a patient has a systolic blood pressure higher than 130, I think they just recently changed this to 120, or a diastolic blood pressure higher than 80, then the patient has high blood pressure. And the question they're saying now, should this person consider taking medication for high blood pressure? So we look at these confidence intervals. It looks like the systolic is fine. It's all underneath 130. With that new rule of, or new limit of 120, this would be above 120. This one here, though, this one looks more of an issue because 78.4 is below 80, this limit here, and 83.8 is above 80. So there is a chance that that diastolic blood pressure is higher on average at higher than 80. So they may want to consider it. They didn't collect very much data, and like with these checks here, we would say we may not fully trust the results of this data. So when you have a conversation with your doctor, you may be like, oh, okay, well, we didn't really collect that much data, and it does seem a little bit high, this upper limit, which could say it's higher than 80, but maybe we should collect more data. So the answer to this question is it really depends on how much data you have. 2 weeks of data is I don't think is quite enough to make a decision to start medication. So you likely want to monitor it, or even just make slight changes in diet, and see if that brings it down a little bit. Maybe try to solve the problem without starting medication. At least that's what I would think. So And I guess, yeah, maybe collect more data is a good answer to that question. I'll write a solution in there. Okay, now one last thing with this section, and it's similar to the last thing we did in section 9.1. We want to find like a sample size that we would need for a certain confidence interval, and it has this formula here which you don't necessarily need to memorize because you can just use the Excel file for this. One thing that's kind of weird with this, and I'm not particularly fond of, it uses a z critical value instead of a t critical value. In your confidence interval, you would use a t critical value. I guess the reason why we can't use a t critical value is because it does change based on the sample size itself. And because of it changing based on the sample size, you can't, like, you would compute something, but then it would change the critical value. So it's like it just wouldn't work without recursion, honestly. So we just end up using the z critical value, but it's a formula that you calculate, and it kind of gives you an estimate of what type of sample size that you would need. So this one says it was determined that the mean weight of salmon had a population standard deviation of 2.15 pounds, and it follows a normal distribution. That's good. How large of a sample should be taken to be 99% confident that the sample mean is within 0.2 pounds of the population mean mu? This very often will be a preliminary check to see if it's feasible to do the study itself. Sometimes you'll do this calculation and then the size of the sample will be ridiculous, and you'll say, okay, that's impossible. Very often you'll have to change what your specifications are for the confidence interval. But yeah, this is kind of a check to do before you actually collect the data, just to make sure it's a feasible study. So just change, we're in the find the sample size for confidence interval, this one, and make sure you're changing the sheet at the bottom. Super important step down towards the bottom there. Make sure you're on mean, and we have 3 different things to fill in. So let me just write here. What we're using. Oh, and I'm on the wrong one. That's all right. So we have to identify the margin of error, the confidence level C, and the standard deviation S. And actually, let me just write the standard deviation here. There we go. Okay, let me show you what I'm writing down. I'm letting that Excel file guide me. We have E, this is our margin of error. And look for that word within. I'm going to put 0.2 in there. The confidence or confidence level is 99%, so 0.99. And the standard deviation, they're using a population one here, which is all right. We put 2.15 pounds in there. Now, one important thing to double check, make sure these have the same units. Sometimes they'll have months, and then they'll give something in days. So you have to convert usually to the smaller unit. So you convert the months into days and then do the calculation that way. But just be careful. Make sure those match. If they are different units, then the calculation doesn't work. So just be very careful with that. We plug those in. And once we plug them in, keep that the same. It gives us 767 salmon. Which is pretty many. I guess it depends on where they're coming from. Out in the wild, that would be, I would think, not feasible. But maybe in like a fish hatchery or something, they might be able to get that many salmon pretty quickly.